So now we're going to go on to balancing some redox reactions. And so when we balance a redox reaction, we actually want to split up the reaction into its half reactions. And so that just makes it easier for us to see the reduction reaction and the oxidation reaction. Then we can balance them and then combine the reactions back together to make it less clunky and just make it flow a lot better, and sort of simplify the process of balancing it. Balancing of these reactions doesn't work very well when you try to just balance them as they are as a whole reaction. So in order to split them up, we first of all want to determine, well, what's being reduced. So we can see that we've got copper going from copper 2+ to copper solid. And so we can see copper solid has a charge of 0, whilst copper 2+ obviously has a charge of +1. So its oxidation number is going from +2 to 0, hence it is gaining 2 electrons, because we're remembering that electrons have a negative charge. So by gaining 2 electrons, it's going from +2 to 0. So we can say the gaining of electrons is reduction, and we're going from copper 2+ to copper solid. So we can write that as our reduction reaction. Next, we need to look at what our oxidation reaction is. So we can say that we've got aluminium, and our aluminium has its charge of 0, and so it's starting off with an oxidation number of 0. It's then forming aluminium 3+, which has a 3+ charge, and hence a 3+ oxidation number. So it's going from 0 to +3, which we can tell means that it is losing 3 electrons. So it's going to be oxidized because it's going from 0 to -3. We're taking away negative charge from it, so we're taking away 3 electrons, and that's going to give us a +3 charge. So we can say our oxidation reaction is aluminium makes aluminium 3+ plus those 3 electrons, because we need to have the charge balanced on both sides. So we can see that with our reduction reaction, we've got copper 2+ and then 2 electrons, so that on this side of the reaction, the net charge of this side of the reaction is equal to the net charge of this side of the reaction, because obviously we've got +2 and then -2. We can add those together, that's going to give us 0, and then this side 0, whilst on this side that's 0, and then we're going to have +3 and -3, gives us 0 on this side as well. So we can see our two reactions were not balanced in terms of their charge between them. So they were balanced, when we look back, we can see they're balanced for each side, but these two reactions are not balanced in terms of their transference of electrons. So if we're to consider our reduction, we've got a transference of 2 electrons. Whilst if we're to consider our oxidation, we've got a transference of 3 electrons. And so if we have a transference of that and they're in the same reaction, there's not an equal transference of electrons. So we need to make sure that it's balanced so that the amount of electrons that are being lost by the oxidation is the same as the amount of electrons that are being gained by the reduction. Because remembering that oxidation reduction with redox reactions is the sharing of electrons. So we need to find the lowest common multiple. So the lowest common multiple between 2 and 3 is going to be 6. So we need to multiply our reduction reaction by 3 and our oxidation reaction by 2. And so when we do that, we then get, we can then add up the reactions together. So we'll end up with 2 copper 2 plus, 3 copper 2 plus 6 electrons makes 3 copper solid, and then we'll end up with 2 aluminium solid makes 2 aluminium 3 plus 6 electrons. And so if we're to add those two reactions together to make an entire one reaction, we can put all the reactants on one side and all the products on the other side. And so when we're to do that, we get 6 electrons plus 2 aluminium solid plus 3 copper 2 plus, and that's going to make 2 aluminium 3 plus 3 copper solid plus 6 electrons. And so now we just want to check that we've balanced it correctly. So we can see we've got 6 electrons on each side, which we can actually cancel out because they're both on each side, so we don't need to specify that they're both there because there's no actual net change between each side. And then with our aluminium, we've got 2 aluminium on this side and we've got 2 aluminium on this side, so that is balanced. Then with our copper, we've got 3 copper on this side and 3 copper on this side, so that is balanced as well. So the final thing that we do is we just cancel out anything which has any double ups. So we've got 6 electrons on each side, so we can cancel those out because we just have a net change in electrons that we don't need to actually show there. So then we end up, as a final redox reaction, we end up with 2 aluminium solid plus 3 copper 2 plus makes 2 aluminium 3 plus 3 copper solid. So now I'm going to let you all have a turn to balance this yourselves. And so I'll give you 4 minutes to do this one on your own and see how you go, and then we'll go through the answer. So yeah, I'll give you 4 minutes for that. Okay, so now we'll go through the answer for this one here. So we've got aluminium solid plus hydrogen ions makes aluminium 3 plus hydrogen gas. So with this one, we first of all need to identify what is being oxidized and what is being reduced. So we've got aluminium, and it's going from 0 because we can see that it's solely just made up of one element, that being aluminium. So that's only that's rule 1, and so it's going to have its oxidation number of 0. Then it goes to a 3 plus charge, which is based on rule 2. So then we can see that if it's going from 0 to plus 3, remembering that electrons have a negative charge, it means that this one is gaining 3 electrons. So it's going from 0 to 3 plus, it's gaining 3 electrons. Then we can look at hydrogen, and so hydrogen, we can see here, the hydrogen atom has a +1 charge, and that's using part B of rule 2. And then we can see hydrogen gas has, using rule 1, has each hydrogen atom has a charge or an oxidation number of 0, and the entire thing is 0 as well. And that's because that's just solely made up of hydrogens. And so we can see hydrogen is going from +1 per hydrogen atom to 0 per hydrogen atom. So that means that, remembering that electrons have a negative charge again, this one is losing, hydrogen is losing 1 hydrogen atom. So 1 electron per hydrogen atom. So we can see that if aluminium is going to be losing 3 electrons, it's going to be being oxidized, whilst if the hydrogen is going to be gaining 1 electron per hydrogen, then it's going to be reduced. So we can write out, we've got 2H plus 2 electrons makes H2, and we've got aluminium plus aluminium 3 plus 3 electrons, and so that's our 2 separate equations. But remembering that we've got a transference of 2 electrons in the hydrogen reaction, which is our reduction reaction, and we've got a transference of 3 electrons in the oxygen reaction, which is oxidation. And so with our reduction reaction, we need to find, in our oxidation reaction, we need to find a lowest common multiple. And so that's going to be 6. So we need to times the reduction reaction by 3 and the oxidation reaction by 2. So that's going to give us 6H plus 6 electrons makes 3H2. And then over here for the oxidation, it's going to give us 2 aluminium plus 2 aluminium 3 plus 6 electrons. So we can put all of the reactants on one side and all of the products on the product side. And so we'll get 6 hydrogens, ions, plus 6 electrons, plus 2 aluminium is going to make 2 aluminium 3 plus 3 hydrogens, plus 6 electrons. And then we can cancel out any double ups that we have on both sides. So we can take out the 6 electrons on both sides, because that's just a net change of 6 electrons from both sides. So we don't need to show it. So then that gives us 2 aluminium plus 6 hydrogen ions makes 2 aluminium 3 plus 3 H2. So now we need to look at how we balance in acidic conditions. And so balancing in acidic conditions is the main condition type which you need to understand. For this, you'll see some places have how to balance in basic conditions, but for the sake of this syllabus and for Unit 3 and 4, you only need to know how to balance in the acidic conditions, not the basic conditions. So these are our main steps which we have for balancing in acidic conditions. So the first thing you need to do is write out the half reactions for each of the parts, so the oxidation and the reduction reactions. So same as you would always do for these. And then the next thing you need to do is balance for all atoms other than oxygen and hydrogen. So that's just your typical normal balancing. So the type of chemical reaction balancing you did in grade 10 and grade 11, just that type of balancing, and balance for all atoms other than oxygen and hydrogen. The next thing you want to do is balance for oxygen by adding water. And so using those oxygens in water in order to balance for oxygen. And then you need to balance for hydrogen ions by adding H+. And so it's really important that you always do step 3 before you do step 4, because if you do step 4 before you do step 3, you then aren't balanced for your hydrogen ions again, because water has the hydrogen in it. That would then disrupt that hydrogen balance. So you balance for oxygen first using water, then balance for hydrogen by using hydrogen ions. The next thing you need to do, which is step 5, is balance the charges by adding electrons to each side. So that's adding just a little E- symbol, and then however many you need, so whether it be 5 electrons or 4, and that's just putting it on whichever side requires more negative charge, so that each side has the same amount of charge on it. The final thing you want to do is make sure that the number of electrons are equal, and then once you've done that, you can add the half reactions together. So that's that process where you get all of the reactants, put them on one side, and then take all of the products and put them on one side. And so often you'll notice when you do that process of adding all the reactants on one side and adding all of the products on the other side, you might have 4 H2O plus 3 H2O plus whatever other compounds, or 5 hydrogen plus 7 hydrogen, and then all your other compounds. And so in that case, you can actually consolidate those. So if you have like 5 hydrogen plus 7 hydrogen on one side, you can actually add those together and just simplify it to being 12 hydrogen. The next thing you also need to do with that step 6 is taking away the electrons which you've added to both sides, so that they're balanced in that you don't have like a net change that's been displayed there. So if you have 5 hydrogen on one side, so 5 electrons on one side and 5 electrons on the other side, you can cancel those out. Same goes for if you've got, for example, 5 hydrogen or 5 water on the left hand side, and you've got like 4 water or 4 hydrogen on the right hand side, you could cancel those out as well. So if you've got 5 water on the reactant side and 4 water on the product side, you can take away the 4 water from the product side, take away 4 water from the reactant side, and that just leaves 1 water molecule on the reactant side and none on the product side. So it's just sort of simplifying out that reaction so that it's displayed more clearly. So we're going to do an example here. So we can see we've got dichromate ions plus chlorine ions makes chromium 3 plus chlorine gas. So our first step we need to do is separate them into their two half reactions, so an oxidation reaction and a reduction reaction. So our oxidation reaction being the chlorine 1 minus makes the chlorine gas, and our reduction reaction being the dichromate ions makes the chromium 3 plus. And so this is because we can see the chlorine is going from 1 minus to 0, because we're looking at part B of rule number 2, that's going to have the charge which is on it as its oxidation number. So that's -1. Then our chlorine is using rule number 1 because it's entirely made up of one element. So it's going to be having its charge of 0. And so hence its oxidation number for each chlorine atom and the entire molecule will be 0. So here we're going from -1 to 0 per chlorine atom. So that means that the chlorine is losing an electron, because we're remembering electrons are negatively charged. So we're going from a negative charge to a more positive charge. And so that means that we've then lost an electron per chlorine atom. Then with our reduction, this one's a little bit different in that we can see we don't have oxygen on the other side of the reaction. We've only got oxygen on the reactant side. So we know it's not oxygen which is participating in this particular reaction, but we do need to look at how the oxygen contributes to this. So we need to go through our rules for this one, in that we can see these dichromate ions have a charge of -2. And so this charge of -2 tells us that this entire molecule has an oxidation number of -2. Next, we know that rule number 7 is going to tell us that oxygen has its oxidation number of -2 per oxygen atom. But we've got 7 of them, so we need to do -2 times by 7, and that gives us -14. And so if we've got -14, but we need to get to -2, and we've got 2 chromium ions, we need to make up +12 out of our 2 chromium ions. And so +12 between 2 chromium ions, we do +12 divided by 2, and that's going to give us +6 per chromium ion. And so we can see our chromium ions are going from +6 to +3. And so if our chromium ions are going from +6 to +3, that means they're gaining 3 electrons. So they're becoming more negative because they've gained 3 electrons per chromium ion, and so hence that is a reduction. So we've got our oxidation reaction and our reduction reaction. So now we need to balance them. So we can see on this side of the reaction, we've got 1 chlorine, and this side we've got 2 chlorines. So we need to balance for those. So we're balancing for everything except oxygen and hydrogen. So we can balance for chlorine, and so that's done for the oxidation reaction. Then we can balance for, in our reduction reaction, we need to balance for the chromium, because we can't balance for the oxygen, because we need to balance for the chromium first. So we can see we've got 2 chromiums on this side, but only 1 chromium on this side. So we need to put 2 in front of this here. So now our reduction reaction is balanced for all elements other than oxygen and hydrogen. The next thing we need to do is balance for oxygen. So we don't need to do that for the oxidation reaction, because the oxidation reaction has no oxygen in it. The reduction reaction, however, does have oxygen, and it has 7 oxygens on the reactant side, but none on the product side. So we need to put 7 water molecules on the product side of the reaction in order to get 7 oxygens on both sides of the reaction. Now we need to balance for hydrogen. So there's no hydrogens in the oxidation reaction, so we don't need to worry about that. However, in our reduction reaction, we didn't have any hydrogens on the reactant side of the equation, but we did have 14 hydrogens on the product side of the reaction. And so we need to get 14 on the reactant side, so both sides are balanced. So we can add 14 hydrogens to the reactant side of the reaction in the form of H+, or hydrogen ions. So we say we've got 14 H+ now on the reactant side. So we've got 14 hydrogens on both sides of the reaction. The next thing we need to do is balance for electrons. So we can see on the oxidation reaction, we've got 2 chlorine on this side of the reaction, and so that's 2 chlorine ions, so 2 Cl-. That means we have a 2- charge on the reactant side of the reaction, but on the product side, if we've only got Cl2, we've not got any charge on this side. So we've got a charge of 0 on this side and a charge of -2 on this side. So in order to balance, we need to add 2 electrons to the product side. So we've got -2 on this side and -2 on this side. Now for the reduction reaction, we can see that we've got 14 plus here, but then 14 plus -2 would give us 12 plus for the reactant side. And then on the product side, we can see each chromium ion has 3 plus, but we've got 2 of them, so the chromium ions have a 6 plus charge. And so we've got 6 plus on this side and 12 plus on this side. So in order to make those balanced and have the same charge on both sides, we need to put 6 electrons on the reactant side, so that we've got 12 minus 6 gives us +6 on the reactant side, and then we've got +6 on the product side. The next thing we need to do is make sure that the reactions are balanced in terms of their transference of electrons. So as we saw before, the oxidation has a transference of 2 electrons, whilst the reduction has a transference of 6 electrons. So in order to make that equal, we need to multiply our oxidation reaction by 3 so that it has the same transference of electrons as the reduction reaction. Because remembering that the oxidation is going to lose electrons to donate to the reduction reaction. So the reduction reaction is going to stay the same, whilst the oxidation reaction has now been multiplied by 3 to become 6 Cl- makes 3 Cl2 plus 6 electrons. So now we've got these fully balanced, we can then take all of the reactants and put them on the reactant side, and all of the products and put them on the product side. So we get 6 electrons plus 14 H plus dichromate ions plus 6 chlorine ions makes 2 chromium ions plus 7 H2O plus 3 chlorine makes 6 electrons. And then we can cancel out what's common on both sides. So we can know that's the 2 lots of 6 electrons. So we can take that off that side and that off that side. And that simplifies it down to our final reaction of 14H plus dichromate plus 6 chlorine ions makes 2 chromium ions plus 7 H2O plus 3 chlorine.